Hi, my name is Nathan Su. Saddleback College Robotics is proud to present our 4th generation rover, Osiris. This year, we organized our team by subsystem, forming the chassis, arm, drive, science, and autonomy subteams.
Our riveted carbon fiber chassis houses a total of 4 lithium-ion batteries, chosen for the high energy density and discharge capabilities. 3 12-volt batteries are connected in parallel to provide 69,000 milliamp-hour capacity for the drive, arm, and science subsystems. To protect against brownouts and power surge failure, a separate 48-volt battery powers all computers and networking electronics on board the rover. Each battery is connected to a battery management system that protects against overcharge and over-discharge. We have designed a kill switch PCB that uses relays and a logic gate, providing both a hard stop and soft stop that can sever all electricity immediately or shut down all motors while preserving computer power. Our antenna includes a spring-loaded folding mechanism to meet weight and size requirements.
Osiris's 5 degree of freedom arm utilizes 2 heavy-duty linear actuators for strong lifting capabilities. The turret azimuth rotation is a hypocycloidal cage pinion and ring gear mechanism that produces high torque with 0 backlash. The turret is modular in application and is reused on our science mission. Our 2-axis end effector actuates using a series of gear trains and worm drive, powered by 3 high-torque DC motors, providing both fine positioning and gripping and heavy lifting capability. We designed a custom PCB integrating 6 closed-loop motor controllers with power and data provisions.
Osiris features a rocker boogie suspension with a rear-mounted differential bar, giving the rover stability over rough terrain. The limbs are square carbon fiber tubes chosen for its high strength-to-weight ratio. The front and back wheels are powered by 400-watt brushless DC motors using 100-to-1 gearboxes, outputting 260 Nm of torque. The wheels are 3D printed thermoplastic polyurethane 250mm tires. For our motor drivers, we are using dual motor controllers with 3-phase Hall effect sensor feedback and integrated PID control loops, capable of up to 120 amps of continuous current.
Our science apparatus features a suite of different tests to determine the presence of life on different sites. The lowering platform mounted at the front of the chassis carries multiple non-intrusive sensors. Using a combination of infrared, ultraviolet, and optical imaging, the fluorescence and spectra reflected off samples are studied for mineral composition and signs of life. Soil samples are vacuumed into a light isolated testing chamber. After experiencing a chemical bath, the sensor measures the luminescence of the ATP in the soil samples. Across the entire science package, 2 boards incorporate MOSFET circuits to control the soil collection mechanism, rotation of testing chambers, and the rock sampling process. For autonomy, point clouds are generated using a Stereolabs Z2i and leveraged on an NVIDIA Jetson AGX Xavier for GPU accelerated computing. Stereoscopic images are parsed for depth points that deviate from an estimated floor plan to detect objects in 3 dimensions. Detected objects and boundaries are then used in an A-star search algorithm to find the shortest path to a given GPS waypoint. Autonomous motor control is facilitated by issuing rotation speed values to a ROS2 service node. Alvar tag detection is implemented using OpenCV and is built in our UCO module. Each Alvar tag has a hard-coded Boolean checkpoint indicating if said tag has been found. Frames with detected tags are transmitted back to the base station for verification.
Base station communications leverage Ubiquiti's 2AC Prism radio and AirMax antenna on the 2.4 GHz radio band, excellent for 9 line-of-sight communication and high bandwidth data streams. Across this point-to-point network, control commands are sent downstream and telemetry is sent upstream via nodes in the ROS2 interface. ROS2's GUI interface RQT is utilized for control buttons for motors and cameras and status signals, process indicators, and video feeds. To control the arm, we use a joystick to get precise pose estimation for the joints of the arm. A Warthog Potas Thrustmaster is used for the drive control to enable manual drive over the network and achieve trajectory motion of the rover.